Hey, so in this tutorial I'm going to show you sort of the logic and the reason behind the row reduction for solving 2 or 3 planes. So what I'm going to do is I'm going to start with a line, something like this, and then we're going to create 2 different planes that contain this line. And then what I'm going to do is I'm going to assume that I never knew the line, never knew what it was, and I'm going to find then the intersection of the 2 planes. And that should give you a pretty good idea of how this row reduction works, why it works. Somewhere in the middle there's a step where we let z equals t, and that's sort of the motivation behind this tutorial, because a lot of students find that to be a pretty uncomfortable step. It's sort of taken in faith that that's what you do, and I'm going to try and show you why you can do that. So let's get started. Alright, so let's start with a line. Just make up a line. We can say that the line is equal to x plus 1 over 2 equals y minus 1, say over 1, and z plus 2 all over 2. And we know that you should know that this Cartesian form is always equal to t. So I'm going to not write this t right now. So what I could do, you should know this, what I could do is there are infinitely many ways to represent this line, right? This is a line, it's got infinitely many points. If I wanted to, I could start to move everything away from z. So if I wanted to, I could multiply everything by 2. It would still be the same line, so then I'd get x plus 1 equals 2y minus 2 equals z plus 2. And then if I wanted to, I could subtract 2 from everything, so I'd get x minus 1 equals 2y minus 4 equals z. Okay, still the exact same line, different form, different rate. You can see that the I'm dividing by 1 on all these now. So, but it's still equal to a t. It's a different t, and you can see now that in this case, the z is equal to t. And this step that we're going to do later that most students have problems with, this is what the problem is. You're not convinced that z is equal to t, but you just have to know that there is a line, so we made up this line, there is a case in which we could rearrange everything and let z and t be paired together. Alright, so like I said, let's build a plane. We're first going to write this equation in vector form. So we'll let L equal, remember this is equal to t, so we'll multiply by 2, so that's 2t for the x, multiply by 1, multiply by 2, and then the x's, I'll subtract 1. Y minus 1 is equal to t, so we'll add 1, and then minus 2. Alright, so now this is a line in vector form. So what I'm going to do now is I'm going to find a plane that contains this line also in vector form. So I'm going to start with the line. So here's the line. Now if I want a plane that contains this line, all I need is another direction. So we'll say S, and we'll just say 1, 1, 1. So now it contains the line, and then it has another direction going off somewhere else, which makes it a plane. Let's make another one. Make sure it contains the line again. Minus 2. And then, whoops, we need another parameter. Typically we use different parameters. So we'll say this is mu, and this is lambda. And let's just say 1, 0, 2. So now we have 2 planes that guaranteed share this line, and that is their intersection. That is their solution. We know that to be true. Okay, so now let's convert both of these planes into Cartesian form. So to do that, we need the cross product, ijk, ij, Okay. The first one we take the two direction vectors, so that's 2, 1, 2, 1, 0, 2. The other one, 2, 1, 2 again, and I believe it was 1, 1, 1. So now if we do the cross product here, start here, 1 minus 2 is minus 1, 2 minus 2 is 0, and then 2 minus 1 is 1. This one we have 2 minus 0 is 2, 2 minus 4, 2 minus 4 is minus 2, and then 0 minus 1 is minus 1. These will now be our coefficients of our vector plane in Cartesian form, so that's minus 1x plus 0y plus 1z is equal to d. And this one is 2x minus 2y minus z is also equal to d. We have to find d now. If you remember, we have one point that's contained in both the planes, minus 1, 1, minus 2. And this one again, same point, minus 1, 1, minus 2. Now we'll go find d. So that will be 1 when I plug in negative 1. That's 0, of course, and then minus 2 will be minus 1 equals d. So this plane is minus x plus z is equal to minus 1. That's this plane. And then this one, minus 2, minus 2 again, plus 2 equals d. Those will go, and we'll be left with minus 2 equals d, which means the plane is 2x minus 2y minus z is equal to minus 2. So let's just recap what we're doing here. What I've done so far is I've made up a line. I've found two vector planes that contain that line. You can see here that the line is right here and right here. I just need two different directions going off somewhere else. Converted them to Cartesian form, each of those planes. So these planes should, unless I made a mistake, still contain this line. And now what I'm going to do is I'm going to solve these two Cartesian equations, and I should get the line again. And it might look a little bit different, but let's just make sure that it is the same line. Okay, so let's go. So how do I do this? I put this in what's called augmented form. So just take the coefficients, negative 1, 0, 1, and then negative 1, and then 2, minus 2, minus 1, minus 2. Okay, I'm going to multiply this top row by 2. So I have minus 1, 0, 1, minus 1. I just write the same row itself without the 2, but I'm going to do the math for this row with the 2. So that's minus 2 plus 2 is 0. 0 minus 2 is minus 2. 2 minus 1. 2 minus 1 is 1. Negative 2 minus 2 is minus 4. Alright, so now here's that step that students take in good faith. Z is equal to t. And we already showed that that is possible. Given this line that we made up, if we rearranged it, there is a case in which z is paired with t, and it will be the same line. It will look exactly the same. So we're going to use z is equal to t. So now it's negative 2y plus z, but z is t, is equal to minus 4. And move everything away from y, and we should get, looks like y is equal to 2 plus 1/2 t, I believe. And then let's do it again for x, so that's minus x plus z, but z is t again, equals minus 1. And we get x is equal to t plus 1. So here's our x's and y's. Here's our z. Okay, so then if I put it in vector form, I get 1 plus t times 1. This will be 2 and 1/2, and this will be 0 and 1. The question is this line the same as the one we started with? Well, you can see right away 2, 1, 2. That's the direction of our original. 1, 1/2, 1. That should be the exact same thing. It's just going half the speed. And then 1, 2, 0. That's a point on this line. Let's go make sure that that point is on this line as well. I can just do it right here. So 1, 2, 0. 1, 2, 0 equals -1, 1 minus 2 plus t, 2, 1, 2. So find the t such that this is 1. So 1 minus, this would be t is -1. If I substitute a -1 here, I'll get 1. If I substitute a -1, do I get 2? Oh, sorry, 1. Sorry, not -1, 1. So -1 plus 2 will be 1. If I plug in 1 here again, I get 2. And if I plug in 1 here, I also get 2, or 0. Which means that they are the same line. Since they have the same direction and they both have this point, they're the same line. I hope that helps. It's a long process, but I think that hopefully helps with that z equals t step and sort of the whole process.